There is a world in our solar system that takes roughly 11,400 years to complete a single orbit around the Sun. Its name is Sedna. Even at its closest, Sedna remains billions of miles from the Sun, far beyond the region where Neptune can easily explain the shape of its orbit. Something appears to have disturbed this world long ago, but astronomers still debate what that something was. And Sedna is not the only problem. Other distant objects have been discovered following enormous, strangely oriented paths through the darkness beyond Pluto. Some of those orbital patterns led astronomers to propose something even larger, hiding farther out, an undiscovered world several times the mass of Earth, Planet 9. Nearly a decade of searching has failed to reveal it, but the mysteries beyond Pluto do not stop with an unseen planet. Quaoar possesses rings where conventional expectations suggested material should gather into a moon. Other distant bodies preserve clues from an ancient solar system we have barely begun to reconstruct. And beyond them lies an even greater wilderness, potentially containing enormous numbers of frozen objects so distant that most have never been observed directly. Pluto once looked like the end of the map. Now it looks more like the beginning. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Now, let's begin. For most of human history, Saturn marked the outer boundary of the known planetary family. You could see it without a telescope, a pale point wandering against fixed stars. Beyond Saturn, the sky offered no obvious planet at all. The map appeared naturally finished. That confidence changed in 1781. William Herschel was surveying the sky through a telescope when he noticed an object that looked unlike an ordinary star. He initially reported it as a comet. Continued observations revealed something far more consequential. Its path belonged to a planet, later named Uranus, moving around the Sun beyond Saturn. The boundary moved again less than 70 years later through mathematics rather than accident. Astronomers had noticed that Uranus was not following its predicted orbit exactly. Its motion seemed to be disturbed by gravity from something unseen. French mathematician Urbain Le Verrier calculated where another planet should be if its pull caused those deviations. In 1846, astronomers at the Berlin Observatory looked near the position Le Verrier predicted. Neptune appeared within about 1 degree of his calculated location. For the first time, an unknown planet had effectively been demanded by orbital mathematics before a telescope confirmed it. We had learned that invisible worlds could reveal themselves through the motion of visible ones. Then came Pluto. In 1930, Clyde Tombaugh discovered the distant object while comparing photographic plates at Lowell Observatory in Arizona. Pluto became the ninth planet and for decades occupied the cultural edge of the solar system. Later measurements showed how small it really was. Pluto is narrower across than Earth's moon. To follow what came next, we need one useful measure of distance. An astronomical unit is the average distance between Earth and the Sun, roughly 93 million miles. Neptune orbits at about 30 astronomical units. Pluto's orbit carries it farther on average. Beyond those distances, sunlight weakens dramatically, and finding small objects becomes increasingly difficult. For much of the 20th century, Pluto seemed almost solitary out there. Some astronomers suspected a population of smaller icy bodies beyond Neptune, but direct evidence remained elusive. David Jewett and Jane Liu spent 5 years searching for one. In 1992, they succeeded. Their discovery was a faint body beyond Pluto, the object now officially named Albion. It was the first confirmed member of a population that observations would soon reveal in growing numbers. The old planetary map had contained a hidden frontier. Pluto was surrounded by frozen neighbors, many occupying paths unlike those of the familiar planets. Jewett and Liu had detected only one small world, yet its existence exposed a vast population beyond Neptune, where the architecture of the solar system becomes stranger with distance. Gravity usually leaves fingerprints. In the outer solar system, astronomers can trace most unusual orbits back to the giant planets. Neptune scattered countless icy bodies outward. Jupiter could eject objects with enormous gravitational kicks. Others became trapped in gravitational resonances, repeating orbital patterns maintained by planetary gravity over immense spans of time. Sedna refuses that explanation. Its closest point to the Sun, called perihelion, lies about 76 astronomical units away. Neptune cannot effectively scatter an object whose perihelion remains so distant. Its strongest influence shapes bodies much closer to its own orbit, while Sedna never approaches within roughly 26 astronomical units of that outer planetary region. The separation matters. No known planet can easily produce Sedna's present orbit under the standard scattering processes that organize most distant objects. Yet Sedna occupies that orbit today. Something altered its path, perhaps during the solar system's earliest history, and then left it stranded far beyond Neptune. Its journey is enormous. Sedna approaches within about 76 astronomical units of the Sun, then retreats to roughly 937 astronomical units. Completing that path requires around 11,400 years. We happen to exist during the portion when Sedna is moving inward toward perihelion, expected around the year 2076. Afterward, it begins another immense retreat. Astronomers Michael Brown, Chad Trujillo, and David Rabinowitz discovered Sedna in November 2003, announcing it publicly in March 2004. Their survey had been searching specifically for distant solar system bodies. The faint object they detected eventually proved stranger than its brightness suggested. Brown's team later discovered Eris, whose existence helped force astronomers to reconsider the definition of a planet and ultimately Pluto's classification. Yet Brown has described Sedna as among the most scientifically important discoveries from those searches. Its orbit preserved information that ordinary trans-Neptunian objects could not. Even Sedna's surface carries evidence of immense isolation. Observations show an unusually red world, among the reddest known large bodies in the solar system. That coloring is consistent with complex organic material, produced when radiation alters carbon-rich ices over extraordinary timescales. Methane has also been identified on its surface. With little evidence for substantial recent resurfacing, ancient material may remain exposed there. So, what moved Sedna? Several possibilities remain scientifically plausible. A star passing near the young sun could have disturbed Sedna during the solar system's birth cluster. Sedna might preserve gravitational effects from an unseen distant planet. Another possibility places its origin around a different star before the young sun captured it during a close stellar encounter. Each explanation requires conditions we cannot yet confirm. Sedna therefore remains a preserved gravitational record with part of its history missing. More distant bodies have since appeared with similarly detached orbits, and their paths show patterns that have made Sedna's isolation part of a larger problem. A single strange orbit can be an accident of history. Several strange orbits sharing the same geometry demand closer attention. By 2014, Chad Trujillo and Scott Shepard had enough distant objects to notice exactly such a pattern. They were studying bodies with extremely elongated paths beyond Neptune. Several shared similar values for the argument of perihelion, an orbital measurement describing how the closest point to the Sun is oriented relative to the object's orbital plane. Instead of spreading randomly through possible orientations, these distant paths appeared grouped together. That was unusual, although the sample remained small. 2 years later, Konstantin Batygin and Michael Brown examined 6 extreme trans-Neptunian objects. These are distant, frozen bodies whose closest approaches remain beyond roughly 40 astronomical units, while their elongated orbits extend much farther outward. Their analysis uncovered more structure than one shared orbital measurement. The 6 objects appeared clustered in the physical direction their elongated orbits pointed. Their orbital planes also showed a related alignment. If you could view those paths together from far above the solar system, they would resemble a coordinated arrangement rather than 6 independently scattered trajectories. Batygin and Brown calculated that the probability of obtaining the observed clustering randomly was about 0.007%, roughly one chance in 14,000 under the assumptions of their analysis. Gravity offered a possible explanation. Their computer simulations showed that a massive planet on a distant, eccentric orbit could preserve such clustering over billions of years. Repeated gravitational interactions would gradually organize certain extreme objects while allowing others to occupy different orientations. The effect requires no direct contact. Each distant passage contributes a minute gravitational adjustment accumulated across enormous stretches of time. The hypothetical planet became known as Planet 9. Early models placed its mass at roughly 5 to 10 times Earth's, although later estimates have refined the possible range. Its orbit could carry it hundreds of astronomical units from the Sun, with one revolution requiring thousands of years. In the original models, its elongated orbit pointed broadly opposite the clustered objects, allowing long-term gravitational interactions to maintain their unusual arrangement. Nothing resembling a photograph accompanied the proposal. Batygin and Brown were careful about that distinction. They had evidence for a gravitational pattern, not a detected planet. We have encountered this method before. An unseen body's gravity can alter other orbits long before telescopes identify the source. Orbital mechanics can therefore function like an indirect detector, revealing mass through its influence across space. Yet 6 objects remain a small statistical foundation. Their discovery locations depend partly on where telescopes searched and where faint bodies were easiest to detect. That makes the clustering both intriguing and vulnerable to observational bias. Planet 9, therefore, occupies an unusual scientific position. Its predicted gravity may already be visible in orbital data, while the world itself remains absent from every confirmed image. Imagine photographing the same patch of sky tonight, then returning months later. Nearly every point of light remains where expected. Somewhere among them, one faint dot may have shifted by an almost imperceptible amount. That dot could be the planet astronomers have spent years seeking. Distance creates the central problem. If Planet 9 lies near 700 astronomical units from the Sun, sunlight reaching it is extraordinarily weak. Light must travel outward, strike the planet, then return across the same enormous distance before entering our telescopes. Each stage reduces what we can detect. A large world can therefore become remarkably faint. Estimates place Planet 9 around apparent magnitude 22 to 25, depending on its size, surface, and position along its orbit. Apparent magnitude measures how bright an object appears from Earth, with larger numbers representing fainter objects. The unaided human eye reaches only about magnitude 6 under excellent conditions. Pluto can appear around magnitude 14. Planet 9 could be thousands of times fainter still. Brightness alone would be manageable with powerful instruments. Movement makes identification harder. Nearby asteroids noticeably change position against background stars between observations. A planet hundreds of astronomical units away creeps across the sky much more slowly. Detecting that motion can require carefully comparing images separated by long intervals. You also need to search the correct sky. Its proposed orbit covers an enormous region, and astronomers do not know exactly where along that orbit the planet would currently reside. Some possible locations overlap the Milky Way's galactic plane. There, dense fields contain immense numbers of stars alongside gas and dust. Automated searches must distinguish one dim, slowly shifting point from crowded backgrounds filled with changing sources and observational noise. Existing surveys add another complication. Telescopes have never examined every region of the sky to equal depth. Weather, observing seasons, telescope latitude, stellar crowding, and survey design all determine where searches become most sensitive. The distant objects used to infer Planet 9 were themselves discovered through surveys with particular observational footprints. That matters because incomplete coverage can create selection effects. A pattern in detected objects may partly reflect where astronomers were capable of finding them. The Vera Rubin Observatory in Chile changes the scale of this search. Its Simone Survey Telescope carries the largest digital camera ever built for astronomy, containing about 3.2 billion pixels. During its decade-long legacy survey of space and time, Rubin will repeatedly photograph much of the southern sky. Repeated coverage is crucial. Instead of relying on isolated deep images, astronomers can compare vast numbers of observations and identify extremely slow motion across years. If Planet 9 lies within Rubin's sensitivity and surveyed region, its movement could eventually separate it from the stellar background. Until then, the absence remains ambiguous. A distant planet may still sit below previous detection limits. Alternatively, the orbital pattern suggesting its existence may contain less information than it first appeared to hold. A pattern can survive every calculation and still arise from the way observations were collected. That possibility sits at the center of the scientific argument over Planet 9. The proposed world remains a hypothesis, supported by intriguing orbital evidence, but challenged by researchers examining how that evidence was assembled. Outer solar system surveys do not observe every direction equally. Telescope location limits accessible sky. Weather removes observing nights. Dense star fields complicate detection. Researchers also choose particular regions according to their scientific goals. Consequently, the catalog of extreme trans-Neptunian objects is shaped partly by where astronomers have looked. This creates observational selection bias. Imagine that distant objects actually occupy every orbital orientation evenly. A survey examining only certain regions could discover a subset appearing clustered, simply because objects elsewhere were never detectable within that survey. The resulting catalog might contain a real observational pattern without representing the underlying population accurately. That concern became especially important as independent surveys added discoveries. In 2021, researchers analyzed objects from 3 well-characterized surveys, including the Outer Solar System Origins Survey. These programs carefully documented where they searched and how sensitive they were, allowing scientists to model the probability of discovering objects with different orbital configurations. Their analysis found the observed distant objects statistically consistent with a uniform underlying distribution. That result challenged the strongest interpretation of clustering, yet it did not establish that every apparent alignment was meaningless. The number of known extreme objects remained small, leaving substantial statistical uncertainty. Konstantin Batygin and Michael Brown have continued arguing that significant structure remains after observational biases are considered. Their analyses use larger collections assembled from multiple surveys and different statistical methods. From their perspective, chance alone still struggles to reproduce important features of the observed orbital distribution. So we encounter a problem common in frontier astronomy. Two careful analyses can begin with incomplete samples and reach different conclusions about what those samples imply. The disagreement depends heavily on survey characterization, which objects qualify for analysis, and how their discovery probabilities are modeled. Other constraints come from direct searches. Infrared surveys have already excluded a range of possible locations and properties for massive distant companions. Planet 9 could remain faint enough, cold enough, or positioned within difficult regions to escape those searches. Each non-detection, however, removes part of the available parameter space. You can see why a larger unbiased catalog matters. A few additional extreme objects can noticeably alter the statistics when the sample itself is small. The Vera Rubin Observatory is expected to discover many distant bodies through a survey whose detection characteristics can be modeled systematically. For now, Planet 9 occupies neither confirmed reality nor discarded speculation. Its case depends on whether an orbital pattern survives as our map becomes less selective. And even if that pattern survives, a distant planet is only one possible source of the gravity shaping it. Suppose the gravity attributed to a distant planet has no planet attached to it. The mathematics would still work. The distant objects would still respond to mass, regardless of whether that mass belonged to a familiar world or something far stranger. In 2019, physicists Jakob Schultz and James Unwin examined that possibility. They proposed that the gravitational influence associated with Planet 9 could instead come from a primordial black hole captured by the solar system during its early history. Primordial black holes remain hypothetical. Ordinary black holes form when sufficiently massive stars collapse, or through later mergers. Primordial black holes would have formed much earlier, during the first moments after the Big Bang. Extreme density variations in the young universe might have compressed small regions strongly enough for gravity to collapse them directly. No primordial black hole has been confirmed. Their possible masses, however, span an enormous theoretical range. One with several times Earth's mass would contain planetary mass inside an extraordinarily small region. Its event horizon, the boundary beyond which light cannot escape, would measure only a few inches across. The familiar grapefruit comparison refers to this astonishing compression. From far away, gravity would reveal no distinction. Place 5 Earth masses in a planet and 5 Earth masses in a black hole, and distant objects respond to essentially the same gravitational field. Orbital measurements alone would therefore struggle to tell which object was producing the influence. We could map its gravitational effects without learning what occupied the center. Finding such a black hole directly would be extraordinarily difficult. It would have no reflective surface and receive sunlight without returning it toward our telescopes. Stephen Hawking showed in 1974 that black holes should emit extremely weak thermal radiation through quantum processes near their event horizons. This phenomenon, called Hawking radiation, has never been directly detected from an astrophysical black hole. For an Earth mass primordial black hole, it would be far beyond present observational capability. So, how could you detect something that produces almost no light? Gravity provides another method. Gravitational microlensing occurs when a compact object passes almost directly between us and a distant star. Its gravity bends the star's light, briefly magnifying the background source. The foreground object can remain completely dark while announcing its presence through this temporary distortion. Future wide field observations, including those from the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, could potentially identify unusual microlensing signatures from compact objects. The idea remains highly speculative. Primordial black holes themselves are unconfirmed, and capturing one into the required solar orbit presents additional questions. Yet the hypothesis is physically testable and grounded in established gravitational theory. Whatever produces the distant orbital structure, gravity records only mass and motion. It does not tell us whether the unseen source has clouds, ice, rock, or an event horizon. Sedna could once be treated as a solitary curiosity. Then another detached world appeared, and another. Each discovery made the outer solar system harder to describe as a collection of isolated accidents. One important object carries the provisional designation 2012V P113. Chad Trujillo and Scott Shepard discovered it during observations with the Dark Energy Camera in Chile. The team informally called it Biden after then Vice President Joe Biden. Its orbit immediately attracted attention. At perihelion, the closest point of its orbit to the Sun, it remains roughly 80 astronomical units away. Its semi-major axis, meaning half the longest dimension of its elliptical orbit, is around 266 astronomical units. Like Sedna, it stays detached from strong gravitational encounters with Neptune. That made two. Trujillo and Shepard argued in 2014 that similarities among these distant orbits could indicate an unseen, massive body influencing them. Their proposal preceded the later Planet 9 model and helped transform detached objects from individual curiosities into a population worth examining collectively. Then came Lalicahanua, initially designated 2015 TG 387. It acquired the informal nickname the Goblin because observations associated with its discovery occurred around Halloween. Its discovery was announced in 2018 by Shepard, Trujillo, and David Tholen. Lalicahanua approaches no closer than about 65 astronomical units from the Sunday. Its orbit stretches vastly farther outward, with estimates placing its semi-major axis beyond 1,000 astronomical units. One revolution may require roughly 40,000 years, although estimates shift as additional observations refine its path. Its orbital orientation was broadly compatible with predictions involving a distant, massive planet. Computer simulations showed that an object resembling Planet 9 could help maintain Lalicahanua's detached orbit across the age of the solar system. Yet one additional object cannot settle the argument. Every discovery changes the statistical picture only slightly. That limitation becomes clearer when you consider how these orbits are measured. Astronomers may observe an extreme trans-Neptunian object for years or decades, while its complete revolution requires thousands or tens of thousands of years. We are reconstructing enormous ellipses from extremely short observed arcs. Additional distant objects continue to expand that catalog, while some proposed extreme members have orbital uncertainties requiring further refinement. Each one can strengthen an apparent pattern, weaken it, or expose a bias that earlier samples concealed. The deeper population remains largely inaccessible. Current telescopes detect only objects bright enough, close enough, and favorably positioned during surveys. Many more detached bodies could occupy distant orbits beyond present detection limits. If a common gravitational influence shaped that hidden population, its work began long before humans measured the first orbit. Those distant trajectories would preserve an ancient architecture written into the solar system across billions of years. The orderly arrangement of planets we see today is an aftermath. Early in solar system history, the giant planets occupied different orbits, surrounded by a massive disk of leftover icy material. Gravity had not finished arranging the system. A major framework for reconstructing that era is the Nice model, named for Nice, France, where several of its developers worked. Published in 2005, the original model proposed that the giant planets underwent a period of orbital instability after formation. Their positions changed dramatically. Jupiter migrated somewhat inward, Saturn moved outward, while Uranus and Neptune shifted much farther from the Sunday. In many versions of this history, Neptune began near 18 astronomical units, before eventually reaching its present orbit around 30 astronomical units. That movement transformed everything it crossed. The primordial outer disk contained far more material than today's Kuiper Belt. As Neptune migrated through it, repeated gravitational encounters scattered icy bodies across the solar system. Some moved inward and encountered other planets. Others gained enough energy to reach elongated, distant orbits. A fraction escaped the Sun entirely and entered interstellar space. The process was chaotic, but gravity preserved structure within it. Neptune trapped some objects in orbital resonances, where their periods became linked to its own. Pluto survives in such a resonance today. Other bodies remained in more stable regions, while countless objects were removed. Earlier versions of the Nice model connected this instability with a proposed late heavy bombardment around 4 billion years ago, when impacts were thought to have surged across the inner solar system. Modern evidence has made that specific timing and sudden spike less certain. Planetary migration remains strongly supported, but researchers now explore histories where instability happened earlier and bombardment declined more gradually. The destruction beyond Neptune was enormous. Estimates suggest the primordial trans-Neptunian disk contained tens of Earth masses. Today's Kuiper Belt retains only a small fraction of that original material. Much was scattered away, while collisions reduced additional bodies into smaller fragments and dust. Some displaced objects traveled vastly farther. Interactions with the giant planets could send icy bodies onto immense orbits. Passing stars and the Milky Way's gravitational influence could then raise their perihelia, preventing later encounters with the planets. Through this combination, an enormous distant comet reservoir could gradually form. When we look at today's detached and scattered populations, we are therefore examining survivors rather than an untouched original arrangement. Their eccentricities, inclinations, and resonances preserve pieces of a dynamical history reconstructed through simulations and observation. Objects, such as Sedna, may require additional influences beyond ordinary planetary migration, including early stellar encounters or an undiscovered distant perturber. Yet they inhabit a region already shaped by profound rearrangement. The dark worlds beyond Pluto belong to the same planetary system as Earth. Their unusual paths preserve the consequences of an early solar system whose architecture shifted before settling into the configuration we inherited. A ring around a small, distant world sounds almost ordinary now. We have found rings around giant planets, dwarf planets, and smaller bodies. Quaoar became remarkable only when astronomers measured where its ring actually travels. Quaoar is a large Kuiper Belt object, roughly 690 miles across. It orbits beyond Neptune and possesses a small moon named Waywatt. During stellar occultations, when Quaoar passed in front of distant stars, astronomers noticed brief additional dips in starlight before and after the main body crossed. Those interruptions revealed orbiting material. In 2023, an international team reported a dense ring around Quaoar. Its location immediately created a problem. The ring circles roughly 2,500 miles from Quaoar's center, much farther outward than conventional ring theory seemed to permit. The reason involves the Roche limit, named for 19th century French astronomer Édouard Roche. This boundary describes the distance within which tidal forces can prevent loose orbiting material from assembling under its own gravity into a larger satellite. Inside that region, particles can remain dispersed as rings. Beyond it, their mutual gravity should increasingly encourage aggregation. Collisions remove orbital energy, fragments gather, and over long periods, the material is expected to form a moon. Quaoar's ring lies far beyond the classical Roche limit. That makes its continued existence difficult to explain through the familiar picture of ring evolution. Given enough time, the particles should have accumulated into one or more satellites. Yet observations show a ring occupying the region where moon formation should be favored. Researchers have investigated several mechanisms capable of delaying that process. One possibility involves the unusual collision physics of extremely cold ice. Near Quaoar, surface temperatures can fall around 360 degrees below 0 Fahrenheit. Laboratory experiments suggest icy particles at very low temperatures may rebound more efficiently during collisions than warmer particles. Bouncing changes everything. If colliding fragments repeatedly separate, instead of remaining attached, growth into larger aggregates becomes much slower. A ring could survive farther beyond the conventional boundary than models based on different particle behavior would predict. Orbital resonances may also contribute. Quaoar's rotation and Waywatt's gravity can create repeating gravitational relationships that influence ring particles, potentially helping maintain particular structures. Researchers continue testing how collisions, particle properties, and resonances work together. A second ring around Quaoar has also been reported, adding another layer to the system. These discoveries suggest the Roche limit remains useful, while the behavior of real rings depends on more than one idealized boundary. For us, Quaoar offers a precise lesson. Familiar gravitational rules still apply in the Kuiper Belt, yet the materials obey those rules under conditions rarely encountered closer to the sunday. At extreme cold, even ordinary ice can change how an entire ring evolves. In May 2026, the James Webb Space Telescope revealed an atmosphere around a small Kuiper Belt object, according to the proposed interpretation of new observations. For a body with weak gravity in such extreme cold, even a tenuous envelope of gas would require an explanation. The evidence came through a stellar occultation. This occurs when an orbiting body passes directly between a telescope and a distant star. Without surrounding gas, the star's brightness should drop sharply as the solid object covers it. then recover sharply when the object moves away. An atmosphere changes those edges. Starlight passing through gas is refracted and absorbed before the solid surface reaches the line of sight. Instead of an abrupt disappearance, the measured brightness can decline gradually. A corresponding recovery occurs as the object clears the star. That pattern can reveal material too thin to image directly. For a small trans-Neptunian body, retaining such material is difficult. Temperatures across the Kuiper Belt can descend toward 360 degrees below 0 Fahrenheit. Volatile substances such as nitrogen, methane, and carbon monoxide may freeze onto surfaces under these conditions. When molecules become gaseous, however, weak gravity can struggle to prevent their eventual escape. Pluto manages a tenuous atmosphere because its gravity and volatile inventory support seasonal cycles of sublimation and condensation. A substantially smaller body provides much less gravitational restraint. Any persistent gaseous envelope would therefore need replenishment, unusual retention conditions, or another mechanism capable of maintaining it. One proposed source is internal heat. Radioactive isotopes incorporated when a world formed release energy as they decay. Uranium, thorium, and potassium-40 can continue producing heat over billions of years. In sufficiently insulated interiors, even modest radiogenic heating can alter volatile ices and potentially drive material toward the surface. If buried ice sublimates, meaning it changes directly from solid into gas, fractures or porous pathways could allow vapor to escape upward. The resulting atmosphere would behave less like Earth's enduring gaseous envelope and more like a continuously replenished exosphere, an extremely thin collection of particles surrounding a body. You would never see such activity from an ordinary photograph. Its signature might exist only in spectroscopy, occultation measurements, or subtle changes in escaping material. That distinction matters across the Kuiper Belt. Small objects have traditionally been treated as deeply frozen remnants whose surfaces preserve ancient chemistry with limited present activity. Internal heating introduces another possibility. Some may still exchange material between their interiors, surfaces, and surrounding space. Because any 2026 result, this recent requires careful confirmation. Atmospheric interpretations must survive continued analysis, independent observations, and peer review. A gradual occultation alone can have competing explanations that researchers must exclude. Still, the underlying possibility changes what we ask of these distant bodies. A frozen surface does not necessarily imply an inactive interior. Every point of light catalogued beyond Neptune represents a successful detection against enormous odds. For each one we see, many more remain below the threshold of our instruments. The Kuiper Belt catalog is therefore less like a census than a sparse sampling of an immense population. Finding these bodies depends largely on reflected sunlight. A Kuiper Belt object must intercept sunlight, reflect enough of it toward Earth, and happen to occupy sky that astronomers survey deeply enough. Beyond 40 astronomical units, those requirements become severe. Small objects receive little sunlight and return even less. Consequently, our inventory favors larger and brighter worlds. Bodies only a few dozen miles across become increasingly difficult to detect systematically, yet smaller objects should vastly outnumber large ones. That means the most populated portion of the Kuiper Belt may also be the portion we understand least. By 2026, astronomers had cataloged thousands of trans-Neptunian objects, while population models suggest vastly greater numbers remain undiscovered. Estimates indicate hundreds of thousands of bodies larger than roughly 60 miles could inhabit the Kuiper Belt, include smaller fragments, and the population may reach hundreds of millions. Their sizes reveal another puzzle. The distribution does not continue smoothly toward smaller bodies. Around 30 miles across, researchers find a noticeable change in abundance. Objects below this scale appear less common than straightforward models of prolonged collisional grinding once predicted. Perhaps countless smaller bodies were pulverized during the solar system's violent evolution. Perhaps the original population formed differently. The observed distribution preserves information about processes we cannot reconstruct completely. Distance produces an even sharper boundary. Near 48 astronomical units from the Sun, the classical Kuiper Belt falls away dramatically. Astronomers call this feature the Kuiper Cliff. Models once suggested that objects should become progressively scarcer with increasing distance. Instead, the observed population declines much more abruptly. Why would a planetary disk develop an edge? One possibility is gravitational clearing by an unseen massive body during the solar system's early history. Another reaches farther backward. The primordial disk of gas and dust from which these objects formed may itself have ended around this region, leaving too little material beyond it to build a comparable population. Observational bias remains part of the discussion. More distant objects are fainter, and certain orbital populations can spend most of their time far beyond easy detection. The Vera Rubin Observatory can test this by repeatedly surveying enormous areas of sky to unprecedented depth, revealing populations earlier searches routinely missed. For now, the architecture remains incomplete. We see a belt containing thousands of known bodies, infer vastly more from statistics, and encounter a boundary whose origin remains unsettled. Even that territory occupies only the nearby outskirts. The Kuiper Belt, scattered disk, Sedna, and the extreme worlds discussed so far remain within roughly 1,000 astronomical units of the Sunday. Beyond that distance, the scale of the solar system changes again. Before we travel farther, distance itself needs a different meaning. The familiar solar system is measured comfortably in minutes and hours of light. Beyond it, even light begins requiring days, months, and eventually years. Sunlight reaches Earth after about 8 minutes and 20 seconds. By Pluto, that same light has traveled for roughly 5.5 hours. At Sedna's closest approach, the journey exceeds 10 hours. Reach 700 astronomical units, near one proposed distance for Planet 9, and sunlight has traveled for about 4 days. Then the scale changes again. At roughly 2,000 astronomical units, near one estimate for the inner Oort Cloud, sunlight needs around 11.5 days. At 100,000 astronomical units, near the cloud's distant outer reaches, the same journey approaches 1 year and 7 months. You can measure those distances another way, through Voyager 1. Launched in 1977, Voyager 1 has spent nearly 49 years moving outward. It travels at roughly 38,000 miles per hour relative to the Sunday. By 2026, it had reached about 170 astronomical units from the Sun, farther than any other human-made object. That achievement barely changes the scale before us. At its present outward speed, Voyager 1 would require roughly 3 centuries to reach 2,000 astronomical units. Crossing the broader Oort Cloud would take tens of thousands of years. Its instruments will have ceased operating long before then. The spacecraft itself can continue, an artifact drifting through regions no functioning probe has explored. Now place another marker beyond it. Proxima Centauri, the nearest star to the Sun, lies about 4.24 light-years away. equivalent to roughly 268,000 astronomical units. If the Oort cloud extends to 100,000 astronomical units, its outer reaches occupy a substantial fraction of the distance separating our Sun from its nearest stellar neighbor. The solar system therefore has no simple edge you could cross like a border. Planetary orbits end long before the Sun's gravitational domain does. Far beyond Neptune, the Sun still influences bodies whose years can span millions of our own. And these numbers describe structure, not imagined voyages. Comets and frozen remnants have occupied these distances throughout nearly the entire age of the solar system. 4.5 billion years have passed, while many completed only a small number of circuits around the Sunday. Human civilization occupies almost nothing on that clock. Even Voyager's journey becomes a brief outward scratch across an enormous map. Sedna once seemed remote because its orbit carried it hundreds of astronomical units away. From here, Sedna belongs to the nearer landscape. Beyond it stretches a reservoir extending tens of thousands of astronomical units, a structure no telescope has directly photographed as a whole. We know it largely through the occasional objects gravity sends inward. Nothing marks the entrance to the Oort cloud. There is no sharp boundary, no sudden concentration of objects. Somewhere around 2,000 astronomical units, the Sun's distant population may simply begin spreading into an enormous reservoir that eventually reaches perhaps 100,000 astronomical units. We have never photographed that reservoir directly. No object has been observed while securely identified as belonging to the distant outer Oort cloud. Its existence is reconstructed from visitors that fall inward. Those visitors are long-period comets. Some require thousands or even millions of years to orbit the Sunday. More importantly, they approach the planetary region from many directions. Their orbital inclinations do not resemble a flattened belt. They suggest an approximately isotropic source, meaning a population distributed in all directions around the Sunday. A vast spherical reservoir explains that pattern. Population estimates vary enormously because astronomers must infer unseen bodies from the comets we detect. Models commonly suggest around 1 trillion icy objects, potentially more. Most are probably small cometary nuclei, perhaps only a few miles across or less. Larger bodies may exist among them. Their journeys could be extraordinary. At sufficient distances, an orbit lasts millions of years. Some objects may have completed only a handful of circuits since the solar system formed. Others could occupy trajectories altered so gradually that their present paths preserve ancient gravitational encounters. Astronomers usually divide this reservoir into two broad regions. The inner Oort cloud, also called the Hills cloud after astronomer Jack Hills, is thought to begin around 2,000 astronomical units and extend outward for many thousands more. Its structure may remain somewhat flattened. Farther away, the outer Oort cloud becomes approximately spherical. There, the Sun's grip is extraordinarily weak. Galactic influences begin competing with solar gravity in shaping orbital evolution. Passing stars provide one source of disturbance. A star moving near the solar system can slightly alter distant cometary paths. Massive molecular clouds, enormous concentrations of interstellar gas and dust, can also perturb loosely bound objects during encounters across the Sun's galactic journey. Even the Milky Way participates. The galactic tide, the broad gravitational pull produced by our galaxy, gradually changes distant comet orbits. Over millions of years, these tiny alterations can redirect an object inward. Then gravity does the rest. A body that spent billions of years far from substantial sunlight begins falling toward the planetary system. As solar heating strengthens, exposed ice changes directly into gas. Dust escapes with it. A coma forms around the nucleus, followed by immense tails. What we call a spectacular comet may therefore be an ancient frozen body, making one brief passage through warmer territory. Sedna occupies an intriguing region inside this architecture. Its extreme orbit has often been associated with the inner Oort Cloud, although its classification remains debated. Before worlds like Sedna were found, this intermediate territory existed primarily in models. Now we have physical objects suggesting that the enormous gap between the Kuiper Belt and distant comet reservoir is populated after all. A long period comet spends almost its entire existence beyond the planets. For centuries, millennia, or longer, its frozen nucleus remains far from strong sunlight. Then some gravitational disturbance alters the orbit. The object begins falling inward, carrying ancient material into a region where we can finally examine it. Astronomers generally define long period comets as those taking more than 200 years to orbit the Sunday. Many are understood to originate in the Oort Cloud. Their ices preserve chemistry from the solar system's formation, protected for immense spans of time before solar heating awakens them. Hale-Bopp offered one extraordinary example. During 1997, it became visible without a telescope and remained prominent for months. Its present orbit lasts roughly 2,500 years. The previous passage through the inner solar system occurred thousands of years ago, and its next return is expected around the year 4385. Human history barely overlaps one orbit. Comet Neowise gave us another glimpse in July 2020. For several weeks, observers could see its bright coma and sweeping dust tail without optical assistance. Its orbit spans several thousand years. When it previously crossed the inner solar system, the human world bore little resemblance to ours. Its next appearance belongs to a future equally remote. These visitors become laboratories as sunlight heats them. Frozen compounds change directly into gas, releasing dust and molecules that telescopes and spacecraft can analyze. Their brief activity exposes material normally inaccessible at enormous distances. The Stardust mission went further. In 2004, the spacecraft flew through material surrounding Comet Wild 2, collecting microscopic particles in a lightweight material called aerogel. Its return capsule reached Earth in 2006. Scientists later identified glycine, the simplest amino acid used by terrestrial life to build proteins, within cometary samples. That discovery showed that biologically relevant organic chemistry existed in primitive solar system material. Comets could therefore have delivered some prebiotic ingredients to the young Earth, although how much they contributed remains an active scientific question. Then, in 2019, astronomers encountered something different. Comet Borisov followed a hyperbolic path, meaning the Sun could never capture it into a closed orbit. It came from interstellar space. Borisov developed a coma and tail, much like familiar comets. Its chemistry showed important similarities to solar system cometary material, alongside differences that revealed another planetary system's history. For the first time, we could study an active comet formed around another star. Oort Cloud comets remain our recurring messengers from the solar system's distant reservoir. They spend nearly all their lives beyond direct observation. Only during their short passages near the Sun do their frozen surfaces erupt into luminous comas and tails. For a little while, An unseen world becomes visible, carrying ancient chemistry across the planetary region before gravity draws it outward again. A planet does not need a sunrise. Across the Milky Way, planetary mass objects travel between stars, unattached to any stellar system. Astronomers call them rogue planets. Some may have formed alone, while others were expelled from planetary systems during periods of gravitational instability. Their true abundance remains uncertain. Estimates range from billions to potentially trillions across the galaxy, depending on how small a world is allowed into the count. Some studies suggest free floating worlds could rival or exceed stars in number. Planet formation itself provides a natural escape route. Young giant planets can scatter one another so strongly that one crosses the gravitational boundary of its star and never returns. That process connects directly with our own history. The early solar system experienced planetary migration and powerful gravitational rearrangement. Any worlds thrown outward with enough speed would have escaped the sun completely. Once released, such a planet could wander through interstellar space for billions of years. Finding these objects is difficult. Without a nearby star, a rogue planet reflects almost no useful light. Young examples can still glow faintly from heat left over from formation. Older ones become much harder to see. Another method is gravitational microlensing, where a foreground object's gravity briefly bends and magnifies light from a more distant star. Then the Orion Nebula complicated the picture. In 2023, observations from the James Webb Space Telescope revealed dozens of free-floating planetary mass candidates there. Several appeared in pairs. Researchers called these systems Jupiter mass binary objects, meaning two bodies comparable in mass to giant planets orbiting each other without an obvious parent star. Estimated masses extend from below 1 Jupiter mass to around 13 Jupiter masses. Their existence presents an unusual formation problem. Ejecting one planet from a star system is straightforward in simulations. Ejecting two while preserving a fragile mutual orbit is much harder. Direct formation from collapsing gas may offer another route, yet producing bodies this small also challenges familiar models. Now, consider what that means for us. The Sun probably formed inside a crowded stellar nursery, where neighboring stars passed much closer than they do today. During such encounters, objects could be exchanged. A free-floating planet, passing at the right speed and geometry, might have been captured into a distant solar orbit. That possibility has been discussed for Planet 9. If such a world exists, capture offers one potential origin, although formation within our system remains possible. A captured planet would carry material assembled around another star, preserved here for billions of years. Exchange works both ways. The young sun could have surrendered worlds during its own unstable beginning. Somewhere in the Milky Way, planets born beside our familiar worlds may still be traveling alone. They would carry the chemistry of the infant solar system across interstellar space, long separated from the star that formed them. By the time astronomers noticed the visitor, its closest encounter was already over. On October 19th, 2017, the Panoramic Survey Telescope and Rapid Response System in Hawaii detected an object racing away from the sunday. Its path revealed something unprecedented. The trajectory was hyperbolic, meaning the sun could never permanently hold it. The object received the Hawaiian name Oumuamua, meaning a messenger from afar arriving first. It had entered from the direction of Lyra. On September 9th, weeks before discovery, it passed about 1/4 of an astronomical unit from the sunday. Then it began climbing outward again, carrying more than enough speed to escape forever. We never obtained a resolved image of its surface. Instead, astronomers watched its brightness change dramatically as it rotated. Those variations suggested an exceptionally unusual shape. Early interpretations favored an elongated body, perhaps between 6 and 10 times longer than its width. Later models showed that a flattened, disc-like form could also reproduce the observations. Neither possibility resembled anything familiar. Then its motion became stranger. As Oumuamua receded, researchers measured a small acceleration beyond the movement expected from solar gravity alone. Comets can behave this way. Sunlight warms their volatile ices, releasing gas that produces tiny thrusts and alters their trajectories. Yet telescopes detected no obvious cometary coma, tail, or jets around Oumuamua. Something appeared to push it, while the usual evidence of cometary activity remained absent. That discrepancy produced several competing explanations. One proposed molecular hydrogen escaping without creating an easily visible signature. Another suggested nitrogen ice, perhaps blasted from the surface of a Pluto-like world around another star. Researchers also considered an extremely porous aggregate of dust, so lightweight that radiation pressure could noticeably alter its motion. Harvard University astrophysicist Avi Loeb proposed the most controversial possibility. He argued that an artificial structure, perhaps something resembling a light sail, should remain among the hypotheses. Most astronomers considered natural explanations far more plausible, and several studies challenged aspects of the artificial interpretation. Still, the available observations never produced a universally accepted identity for the object. That limitation matters. Oumuamua was discovered late, observed briefly, and was already fading rapidly. No spacecraft could reach it in time. No sample could be collected. Even its precise shape remained indirect. Now the object continues outward, beyond practical observation. You can imagine how little information crossed our instruments during that short encounter. Humanity recognized the first known interstellar object only as it was leaving. For a few weeks, matter formed around another star passed through our planetary system. We measured its light and trajectory, debated its composition, and watched it fade. Whatever Oumuamua truly was, the evidence departed with it. For billions of years, two ancient bodies remained joined at the solar system's distant edge. Then, for a few hours, a spacecraft from Earth passed close enough to reveal their shape. On January 1st, 2019, New Horizons encountered Arrokoth, the most distant object ever explored at close range by a spacecraft. The flyby occurred at 12:33 in the morning, Eastern Time. New Horizons was about 4 billion miles from Earth. Even confirmation could not arrive quickly. Radio signals required roughly 6 hours and 8 minutes to cross the distance to mission controllers at the Johns Hopkins Applied Physics Laboratory. What eventually appeared in the returned images looked unlike a conventional world. Arrokoth is a contact binary, an object formed from two distinct lobes physically joined together. The larger lobe is named Wenu. The smaller is called Weo. Between them lies a narrow connecting region. Their arrangement preserves something extraordinary. Evidence suggests the lobes formed nearby, within the same collapsing cloud of small primordial material. Pebble accretion, the gradual gathering of tiny solid particles into larger bodies, helped assemble objects like these during the solar system's infancy. Wenu and Weo later approached each other at remarkably low speed. Their merger was gentle enough to preserve both lobes rather than destroy them. That geometry changed ideas about early planet formation. Violent collisions were once emphasized heavily in models of how small bodies grew. Arakoth showed that at least some planetesimals, the small building blocks from which planets emerge, could assemble through much gentler processes. Its surface carries another record. Arakoth appears broadly reddish, consistent with complex organic material altered by radiation over immense spans of time. Such substances, often called tholins, can form when simple carbon bearing compounds are chemically transformed by energetic radiation. Impact features exist, but the surface shows remarkably little evidence of destructive processing. There is no sign of the extensive geological renewal familiar on larger active worlds. Arakoth has remained comparatively preserved since the earliest stages of solar system history. When you look at its contours, you are seeing structure inherited from more than 4.5 billion years ago. Earth had not yet developed oceans, continents, or an atmosphere resembling the one above us today. The giant planets had not completed the rearrangements that later transformed distant regions of the solar system. New Horizons crossed this ancient scene at roughly 32,000 miles per hour. Its closest encounter lasted only hours. Cameras and instruments gathered hundreds of observations before the spacecraft continued outward. Arakoth remained behind, following the orbit it had occupied across almost the entire age of the solar system. 4.5 billion years of preservation met a human spacecraft for a few hours, and those hours gave us a surviving physical record of how worlds began. No human instrument has ever examined the Kuiper Belt from closer range than New Horizons. It remains there today, carrying instruments through a region once accessible only as faint points of light. Its journey began on January 19, 2006, from Cape Canaveral, Florida. Speed defined the mission immediately. New Horizons crossed the moon's orbital distance in about 9 hours. Apollo crews required roughly 3 days. After crossing the asteroid belt, the spacecraft reached Jupiter in February 2007 and used the giant planet's gravity to reshape its trajectory. That maneuver increased its speed by roughly 9,000 miles per hour and shortened the journey to Pluto by about 3 years. Pluto arrived in view on July 14, 2015. The images overturned expectations. Across Pluto stretched Sputnik Planitia, a vast basin filled largely with nitrogen ice. Its surface is divided into broad cells created by convection, where warmer ice rises while colder material sinks. Along its margins stand mountains built from water ice, some reaching roughly 11,500 feet above surrounding terrain. Above them hangs a remarkably layered atmosphere. Nitrogen dominates, accompanied by methane and carbon monoxide. Atmospheric haze extends high above the surface, scattering sunlight in ways that produce blue coloration. Pluto, once imagined as a comparatively inert frozen body, showed active geology and evolving surface materials. Evidence also supports another possibility beneath its crust. Models of Pluto's interior allow for a subsurface ocean of liquid water, insulated beneath thick ice and sustained partly by radioactive heating within the rocky interior. Such an ocean could persist without meaningful warmth from sunlight. New Horizons kept going. By July 2026, the spacecraft was roughly 6 billion miles from Earth and remained healthy. Radio transmissions required more than 8 hours to travel one way. After emerging from a 321-day hibernation in June, its instruments resumed broader observations of the distant environment. Its work now measures conditions no nearby spacecraft can sample. Instruments record charged particles, hydrogen in the outer heliosphere, and microscopic dust, These measurements help reveal how the sun's influence changes across distances where planetary exploration has rarely reached. Electrical power comes from a radioisotope thermoelectric generator. Heat released by radioactive plutonium is converted into electricity, allowing the spacecraft to function where solar panels would be impractical. Current planning indicates useful operations could potentially continue into the 2040s as available power gradually declines. There is no comparable replacement already traveling behind it. When New Horizons eventually stops operating, its trajectory will continue regardless. The spacecraft will remain a human artifact moving outward through the galaxy. What it has already shown us reaches beyond Pluto itself. One spacecraft transformed distant points into landscapes, atmospheres, geology, and measurable environments. Those discoveries changed what we can reasonably expect around other stars, where similar planetary systems have followed histories of their own. If you could place our solar system beside thousands of others, one absence would become obvious. Between Earth and Neptune, we have no intermediate planet. Around other stars, worlds in that broad range appear again and again. Astronomers have now confirmed more than 6,000 planets beyond the solar system. Among the most frequently detected classes are super-Earths and sub-Neptunes. A super-Earth is more massive than Earth, but substantially lighter than Neptune, and the name says nothing about whether its surface is rocky. Sub-Neptunes are somewhat larger worlds, often wrapped in deep atmospheres. Our planetary family contains neither class. That makes the proposed Planet 9 especially interesting. Estimates commonly place its mass several times above Earth's, potentially within the super-Earth or sub-Neptune regime. If such a planet eventually appears in distant survey images, the architecture around our Sun would suddenly resemble a pattern already familiar elsewhere. The comparison becomes stronger beyond individual planets. Young stars are surrounded by protoplanetary disks, broad structures of gas and dust where planets and smaller bodies assemble. In their colder outer regions, volatile compounds freeze readily onto grains. Water, methane, ammonia, and carbon-bearing material become part of the ingredients available for distant worlds. We find that same chemical vocabulary in the Kuiper Belt. Its icy bodies preserve water ice, methane, ammonia, and complex organic compounds. Their compositions are therefore pieces of a much wider process. Gravity gathers material. Temperature determines what can freeze. Collisions, migration, and scattering then rearrange what forms. Interstellar comet Borisov gave us a rare physical comparison. When it entered our solar system in 2019, astronomers measured water and several familiar cometary molecules. Some properties resembled local comets closely. Others, especially its unusually abundant carbon monoxide, revealed important differences. Together, those measurements showed recognizable comet chemistry operating around another star without requiring that every planetary system produce identical objects. This changes how we interpret the distant bodies around our own Sunday Pluto, Arrokoth, Sedna, and the countless unseen objects beyond them belong to processes that accompany planetary formation across the galaxy. Other systems should possess their own icy reservoirs, scattered populations, wandering comets, and worlds displaced by migrating planets. Some architectures will look nothing like ours. Others may contain arrangements we almost recognize. From Earth, the familiar planets can make our system seem like the natural template. Exoplanet discoveries reversed that perspective. Nature builds planetary systems with enormous variety, while repeatedly using the same ingredients and gravitational rules. The warmer inner solar system, where sunlight remains strong and one inhabited planet circles its star, occupies only a small portion of that architecture. Across the Milky Way, planetary formation extends far beyond such regions. Most worlds may never receive names or visitors. Many will remain cold, distant, and unseen. In the galaxy's planetary systems, darkness occupies far more territory than daylight. Life at the edge of the solar system would have nowhere comfortable to stand. On the exposed surfaces of distant Kuiper Belt objects, temperatures can fall near minus 364 degrees Fahrenheit. Sunlight is extremely weak. Water remains frozen, and familiar photosynthesis becomes impractical. For biology resembling anything on Earth, the surface offers almost nothing. The interior is different. Large icy worlds can carry energy sources that do not depend on sunlight. Pluto is one of the strongest examples. Evidence from its geology and thermal evolution has made a subsurface ocean a serious possibility buried beneath a shell of water ice. Such an ocean could remain liquid through heat released inside the world. That heat comes partly from radioactive elements within rocky material. Uranium, thorium, and potassium 40 decay over immense periods, releasing energy as they transform. Distance from the sun hardly matters to this process. A world can receive little sunlight and still remain warm deep inside. That possibility extends beyond Pluto. Eris, roughly 1,445 miles across, contains substantial rock beneath its frozen exterior. Makemake, Haumea, and Quaoar may also retain enough internal heat for complex interior histories. Whether liquid reservoirs survive within any of them remains unknown. We have never placed instruments close enough to probe their depths. Recent evidence for activity among smaller distant bodies makes the question broader. If internal heat can move volatile material upward through ice, then these worlds may contain chemical gradients, differences in composition and energy that can power reactions. On Earth, organisms exploit such gradients in environments where sunlight never reaches. That does not mean life exists there. The distinction matters. Liquid water, useful chemistry, and an energy source create possibilities for prebiotic chemistry, the reactions that can precede biology. They do not guarantee biology itself. Another ingredient already covers many outer worlds. Tholins are reddish organic materials created when energetic radiation alters simple carbon-bearing compounds in ice. We see their spectral fingerprints and characteristic colors across bodies such as Pluto and Arrokoth. Laboratory experiments show that related irradiated organic mixtures can yield amino acids after interaction with liquid water. So imagine what we still cannot examine directly. Beneath miles of ancient ice, radiogenic warmth may persist beside organic material assembled before the planets finished forming. Perhaps water once circulated there. On some larger bodies, perhaps it still does. At 80 astronomical units, the sun provides little warmth, yet chemistry does not require a welcoming sky. The ingredients can be scattered into places no spacecraft has touched. Whether they ever combine into something capable of metabolism, replication, or evolution remains unanswered. We know the universe distributes chemistry widely. What that chemistry becomes inside an unvisited, frozen world, far beyond the familiar planets, we genuinely do not know. For most of human history, the outer solar system was mapped through isolated points of light. The coming surveys change that rhythm. Instead of finding distant worlds one at a time, astronomers are entering an era when enormous regions of sky can be repeatedly searched with unprecedented sensitivity. The Vera Rubin Observatory in Chile sits at the center of that change. Its legacy survey of space and time uses a camera containing roughly 3.2 billion pixels. Over 10 years, the observatory will repeatedly photograph the accessible sky, revealing objects through their movement between exposures. That repetition matters enormously beyond Neptune. Thousands of new trans-Neptunian objects could emerge from the survey, including bodies too faint for earlier searches. Extreme trans-Neptunian objects will receive particular attention because their unusual orbits preserve evidence of unseen gravitational influences. Planet 9 faces its strongest observational test here. If a distant planet occupies the brighter portions of the predicted search region, Rubin could detect it directly. Continued absence would progressively restrict where such a world could hide. Eventually, the hypothesis itself would face increasing pressure. Another powerful observer is almost ready. The Nancy Grace Roman Space Telescope is scheduled to launch in August of 2026, bringing wide-field infrared observations above Earth's atmosphere. Its surveys will examine enormous numbers of faint objects while also searching for gravitational microlensing, the temporary brightening produced when an unseen mass bends light from a background star. That technique can reveal bodies producing almost no light themselves. In principle, sufficiently sensitive observations could even constrain exotic possibilities such as a primordial black hole, a hypothetical black hole formed during the universe's earliest moments. Such an object has occasionally been proposed as an alternative explanation for the distant gravitational influence attributed to Planet 9. Meanwhile, the James Webb Space Telescope continues examining individual outer worlds with extraordinary sensitivity. The recent atmospheric evidence around the small trans-Neptunian object known as 2002 XV93 showed how much can remain hidden until instruments become precise enough to notice it. Future observations can test atmospheres, surface chemistry, volatile ices, and thermal behavior across more distant bodies. Spacecraft exploration remains slower. The interstellar probe concept, developed by researchers at the Johns Hopkins Applied Physics Laboratory, envisions sending an instrumented spacecraft beyond 200 astronomical units. Such a mission remains a concept rather than an approved flight, but existing studies show that direct exploration far beyond the planets is technically possible. Since 1992, improved instruments have repeatedly expanded the known outer solar system. Each generation has exposed populations, the previous one barely detected, along with structures its models did not fully anticipate. Now the search is becoming systematic. You can imagine the difference. Instead of wondering whether the darkness contains another Sedna, another unusual ring, or an unseen planet, astronomers will repeatedly measure vast portions of that darkness. The map will become denser. Some mysteries may disappear, others may deepen. The next decade will not merely add names to a catalog, it will test whether the architecture we have assembled from scattered discoveries actually describes the solar system we inhabit. Before a distant world receives a name, it exists for us as a string of characters. Survey teams assign provisional designations according to formal astronomical rules, useful for cataloging discoveries without pretending we already understand them. The system is precise. Yet eventually, some objects become familiar enough to acquire something more human. Sedna received a name drawn from Inuit tradition. Sedna is a powerful figure associated with the Arctic Sea, dwelling beneath frigid waters in several versions of her story. When astronomers announced the distant object in 2004, its extraordinary remoteness made the association especially fitting. A world traveling through one of the coldest known regions had been connected, through language, with an ancient story shaped by cold and distance. Quawar carries another relationship between place and discovery. Its name comes from a creation figure in the traditions of the Tongva people, whose ancestral homeland includes the Los Angeles basin and surrounding region. The object was discovered using the Samuel Oschin telescope at Palomar Observatory in Southern California. Naming it Quawar connected the discovery with indigenous history, rooted in that broader landscape. Makemake followed a different thread. Astronomers discovered the dwarf planet in 2005, shortly after Easter. Its eventual name came from Makemake, a creator figure central to Rapa Nui traditions on Easter Island. A calendar coincidence became part of an astronomical identity now used around the world. Haumea's name extends beyond a single body. Named for the Hawaiian goddess associated with fertility and childbirth, Haumea is accompanied by moons named Hi'iaka and Namaka, figures connected with Haumea in Hawaiian tradition. The names form a related family across an actual gravitational system. Before official naming, however, discovery teams often use nicknames. Some remain memorable long after formal designations take over. The object later named Arakoth was once informally called Ultima Thule, a term whose historical associations generated controversy. After consultation with Powhatan tribal elders and representatives, the mission team proposed Arakoth, a word meaning sky in the Powhatan and Algonquian languages. The International Astronomical Union approved the name in 2019. Other distant discoveries have carried temporary nicknames, such as the Goblin and Biden. These labels belong to the working culture of discovery when an object is known well enough to discuss but has not yet received a permanent identity. You can see something revealing in that progression. First comes detection, perhaps only a few faint pixels moving against background stars. Then measurements accumulate. An orbit appears. Characteristics emerge. Eventually, language catches up. These bodies needed no names during the 4.5 billion years before anyone detected them. Their surfaces formed, their orbits evolved, and their seasons passed without human vocabulary. Naming changes nothing about the worlds themselves. It changes our relationship with them. A designation records that something was found. A carefully chosen name can acknowledge culture, geography, mythology, history, and the people connected with the place of discovery. Across billions of miles, that act becomes remarkably simple. We have seen you. We know you are there. A boundary sounds simple when drawn on a map. Space offers nothing so convenient. Around the sun, several different influences extend outward, weakening at different rates, and each produces a scientifically reasonable answer to where our solar system ends. The first boundary belongs to the solar wind, the continuous flow of charged particles streaming from the sunday. This expanding plasma creates the heliosphere, an enormous region shaped partly by the sun's motion through surrounding interstellar material. Eventually, that outward pressure loses the contest. The transition is called the heliopause, where the solar wind meets the surrounding interstellar medium. Voyager 1 crossed the heliopause in August 2012 at roughly 121 astronomical units from the Sunday. Voyager 2 followed in November 2018, crossing at about 119 astronomical units. By this definition, both spacecraft have entered interstellar space, yet neither has escaped the sun's gravity. That distinction changes everything. If we define the solar system through gravitational control, its boundary moves enormously farther outward. The Sun continues holding distant objects across the Oort Cloud, where orbital periods can stretch across millions of years. Near its outermost reaches, roughly 100,000 astronomical units away, the gravitational influence of passing stars and the Milky Way becomes increasingly important. Here, membership becomes less obvious. A small gravitational disturbance from another star can alter an object's orbit enough to send it inward, push it farther outward, or remove it from the Sun entirely. The solar system at these distances is less a compact planetary arrangement than an immense gravitational domain embedded within the galaxy. A third definition asks something even harder. Where is the most distant object still gravitationally bound to the Sun? We cannot answer that yet. No telescope has mapped the outer Oort cloud directly. Its smallest inhabitants would be extraordinarily difficult to detect, while larger bodies could remain unseen because they receive almost no useful illumination. Their orbital motion across our sky would also be remarkably slow. An undiscovered world could therefore occupy a vast orbit far beyond anything currently cataloged. So you can place the solar system's edge near 120 astronomical units around the heliopause. You can place another meaningful boundary near 100,000 astronomical units among the distant reaches of the Sun's gravitational domain. Or you can admit that the orbit of the last bound object remains unknown. None of these answers cancels the others. They measure different things. Perhaps that is the most accurate way to picture where we live. Nature provides no wall surrounding the Sun's territory. Solar particles diminish. Magnetic influence changes. Gravitational control weakens as neighboring stars and the galaxy exert greater influence. The solar system does not finish at a gate. It becomes progressively less solar, spreading into a region where the Sun is increasingly one gravitational presence among many. Somewhere across that immense transition, the familiar idea of our system gives way to the wider galaxy, without any single point where one can say it has definitively ended. There are clocks in the solar system that never tick. They move instead, tracing enormous paths whose duration can be measured against entire chapters of human existence. Sedna is one of them. One journey around the Sun takes roughly 11,400 years. The last time Sedna occupied this region of its orbit, humanity was entering the Neolithic period. Permanent settlements were beginning to appear. Writing did not exist. Across northern Africa, the Sahara contained grasslands, lakes, and rivers beneath a wetter climate. Sedna kept moving. Another distant body, nicknamed the Goblin, requires roughly 40,000 years to circle the Sunday. When it last occupied a comparable place along that path, modern humans were spreading through regions, including Australia. Neanderthals still survived in Europe. In Sulawesi, people were creating some of the oldest known figurative cave art. The Goblin has not completed one orbit since then. Other distant objects carry similarly immense calendars. 2021 R205, may require more than 20,000 years for a single revolution, depending on refinements to its orbit. Its previous perihelion, the point where an orbit comes closest to the Sun, occurred before the last glacial maximum transformed much of the northern world beneath enormous ice sheets. These are ordinary orbital periods out here. Gravity simply works across distances so large that a year becomes almost meaningless. Consider what happens during one revolution. Languages emerge and disappear. Cities rise from settlements, expand, and become archaeological layers. Borders move, religions spread. Technologies reshape daily existence. Civilizations preserve fragments of themselves in stone, clay, metal, and eventually electromagnetic signals. Meanwhile, Sedna advances through another portion of its orbit. From that perspective, recorded history occupies only a minute fraction of an orbital arc. Even the oldest, surviving written accounts represent a short interval beside the journey of one distant world. That comparison does not diminish anything humans have made. It gives these orbits their proper scale. We usually understand time through lifetimes, generations, and centuries. Beyond the familiar planets, celestial mechanics offers another clock, one whose hands require civilizations to move visibly. You could watch Sedna throughout an entire human lifetime and witness only a small part of its path. Generations could inherit the same observation, each adding measurements to something no individual observer could ever follow around the Sunday. Yet distance does not completely erase connection. Stand somehow upon Sedna during the long passage through its remote orbit, and the Sun would no longer resemble the overwhelming disk seen from Earth. It would appear as an exceptionally bright point among the stars, still dominant enough to mark the center of Sedna's immense gravitational journey. Around that distant yellow-white point circles a small world, and there, during one fleeting moment of Sedna's 11,400-year passage, someone may be lying beneath Earth's night sky, listening while we measure our brief human time against a world that moves by millennia. Standing on Sedna would begin with a contradiction of scale. Beneath you is a world bound to the sun, yet sunlight scarcely illuminates its surface. At perihelion, Sedna approaches only about 76 astronomical units from the Sunday. Even there, noon would resemble deep terrestrial night more than daylight. The sun would span roughly 1/76th of the apparent diameter we see from Earth. Its light would be diminished by the inverse square law, leaving Sedna with roughly 1/5776th of Earth's solar illumination. It would still dominate every star. Looking directly toward it would remain hazardous to human vision. Warmth is another matter. Sedna's surface temperature is estimated near -400 degrees Fahrenheit, depending on location and orbital position. Nitrogen, methane, and other volatile compounds that behave differently on warmer worlds can remain frozen there. Sunlight reaches the ground, but contributes very little heating. Sedna rotates once in roughly 10 hours. That gives you alternating periods facing toward and away from the sun far faster than its immense year progresses. With essentially no substantial atmosphere known, there would be no familiar blue vault overhead, no colored twilight, and no atmospheric shimmer around stars. The sky would remain black wherever you looked. Stars themselves would appear exceptionally sharp to an unprotected optical instrument. The Milky Way would retain the same broad celestial structure visible from Earth because 76 astronomical units is negligible beside galactic distances. Sedna changes our position within the solar system enormously, yet barely changes our viewpoint within the galaxy. Gravity would also reshape every movement. Sedna is roughly 600 miles across, and estimates of its mass remain uncertain. Its surface gravity would be only a small fraction of Earth's. An object released from your hand would fall more slowly, while each step could carry you farther than the same effort would at home. Then there is the year. Sedna requires roughly 11,400 Earth years to complete one orbit. Near perihelion, you would be standing around the closest portion of an orbital journey whose next comparable return belongs to a future beyond recorded history. From there, Sedna gradually travels outward for thousands of years toward aphelion, more than 900 astronomical units away. At that extreme distance, sunlight would weaken drastically again. The sun would remain the brightest star in Sedna's sky, although reduced to a brilliant point whose warmth would be effectively absent at the surface. No weather would move above you. No breathable air would surround you. Every condition follows from measurable properties: distance, rotation, gravity, radiation, and temperature. No human is likely to stand there for centuries. Yet we do not need fiction to construct the scene. The orbit tells us where the sun appears. Physics tells us how much light arrives. Spectroscopy constrains the surface. From those measurements, Sedna already gives us the outline of standing at the farthest reaches of the Sun's planetary family. An object does not enter reality when a telescope finds it. Discovery changes our knowledge while the object itself continues along the path gravity gave it. This distinction matters especially beyond Neptune, where much of the solar system remains known through effects rather than photographs. Consider Planet 9. If such a world exists, its present uncertainty belongs entirely to us. Somewhere along its predicted orbit, a planet several times Earth's mass would already possess a surface, an interior, a temperature, and a gravitational field. It would have completed its history without waiting for a human name. Neptune offers a useful precedent. Before its observation in 1846, astronomers noticed that Uranus was moving differently from predictions. French mathematician Urbain Le Verrier calculated where another planet should be. Johann Gottfried Galle then observed Neptune near the predicted position from the Berlin Observatory. Neptune had been physically present throughout the centuries when nobody knew where to look. The outer solar system extends that lesson across an extraordinary population. Astronomers infer the Oort Cloud from long-period comets arriving on trajectories consistent with a vast, distant reservoir. Estimates place perhaps 1 trillion icy bodies there, yet no individual object has been confirmed through direct imaging as an Oort Cloud member. Think about what that means physically. Those inferred bodies would have shapes, rotations, compositions, scars, and individual orbital histories. Some may have companions. Others may preserve material from the solar system's formation. Each would occupy a particular location at this moment, although we cannot point to it in an image. This creates a different kind of uncertainty from many cosmic mysteries. Dark energy is inferred through the accelerating expansion of the universe. Quantum fields are described mathematically through theories tested by experiments. Beyond the known planets, many unanswered questions concern literal destinations, places a spacecraft could in principle approach if we knew their coordinates and could survive the journey. Our limitation is therefore partly one of scale. Human astronomy has existed for only a thin interval compared with the age of these bodies. Sensitive digital surveys are younger still. Even reflected sunlight needs time to cross the distances involved, while the faint objects themselves can require years of repeated observations before their motions become clear. Nothing out there needs to conceal itself. A frozen body hundreds or thousands of astronomical units away may simply reflect too little sunlight for today's surveys to distinguish it from the background. Its orbit continues regardless. And that is the weight of the unseen outer solar system. When we look into those remote regions, absence from an image does not necessarily mean absence from space. Beyond the reach of present observation, gravity may still be carrying entire worlds around the same sun that lights our sky. 34 years is barely enough time for one generation to grow up. Yet that span contains almost everything humanity has learned about the population beyond Neptune. In 1992, astronomers David Jewett and Jane Liu announced the discovery of 1992 QB1, the first object found beyond Pluto and Charon since Pluto's discovery. The map changed rapidly after that. Pluto ceased to look like an isolated frontier world. Thousands of trans-Neptunian objects entered astronomical catalogs. The Kuiper Belt emerged as a broad population. The scattered disk revealed bodies thrown onto elongated paths. Sedna exposed an even more distant orbital regime, while extreme trans-Neptunian objects gave astronomers a new gravitational puzzle. Then humanity sent something there. New Horizons crossed the Pluto system in July 2015 and continued onward to Arakoth, transforming points of light into landscapes and physical worlds. Yet one successful spacecraft passage also reveals how little territory we have actually examined directly. No spacecraft has explored the scattered disk. None has approached Sedna. No probe has entered the Oort Cloud. Voyager 1 remains humanity's most distant spacecraft, more than 160 astronomical units from the Sunday. That achievement is enormous by human engineering standards. Against the scale of the outer Oort Cloud, however, its journey has barely begun. Even after nearly half a century of flight, Voyager 1 has crossed only a tiny fraction of the Sun's possible gravitational domain. Now compare those decades with 4.5 billion years. Every distant body catalogued during our lifetimes had already completed its history long before telescopes existed. Their surfaces accumulated radiation damage, collisions altered some orbits, giant planets rearranged others. Comets waited through immense intervals before gravitational disturbances sent them inward. We arrived very recently, carrying detectors sensitive enough to notice the evidence. That makes our present knowledge resemble a first inventory rather than a completed map. The true population of extreme trans-Neptunian objects remains uncertain. Planet 9 remains unresolved. Individual members of the Oort Cloud remain beyond direct confirmation. Large distant bodies may conceal internal structures that remote observations cannot yet determine. New surveys will enlarge the sample, and better telescopes will test patterns that currently rest on small numbers. Some proposed worlds may disappear under stronger statistics. Others may become unavoidable. That is how the boundary of knowledge moves. You and I happen to live during this unusually early interval. The first Kuiper Belt discoveries are still within living memory. The only spacecraft to visit that region is still operating. Many fundamental questions remain open enough that observations made within a single night can still alter the architecture we assign to our own planetary system. 34 years open the threshold. Beyond it lies a region whose exploration has scarcely begun. Take away the distance for a moment, and the outer solar system becomes chemically familiar. Water ice coats many of its bodies. Methane, ammonia, and carbon monoxide appear across frozen surfaces. These substances belong to the same chemistry we encounter much closer to home. Even the reddish material, covering many distant objects, follows familiar rules. Radiation transforms simple carbon-bearing compounds into complex organic mixtures, called tholins. Their precise chemistry varies with the starting materials and environment, yet they are built largely from carbon, hydrogen, and nitrogen, elements central to amino acids, proteins, nucleic acids, and living cells. That resemblance has a common origin. About 4.5 billion years ago, The solar system emerged from a collapsing cloud of gas and dust. Material gathered toward the center and formed the Sunday. Around it, a rotating disk supplied the ingredients for planets, moons, asteroids, comets, and smaller bodies. Temperature helped determine where those ingredients accumulated. Close to the young sun, heat favored rock and metal. Farther outward, colder conditions allowed volatile compounds to freeze and remain incorporated within growing bodies. Gravity then rearranged much of what formed. We belong to that same process. The oxygen in Earth's oceans, the carbon incorporated into organisms, and the hydrogen inside every molecule of water trace their histories into material that existed before our planet. The distant objects carry related ingredients, preserved under radically different conditions. Aerokoth makes that connection unusually tangible. Its gently joined lobes preserve evidence of low-speed assembly in the early Kuiper Belt. Since formation, it has avoided the extensive heating and geological recycling that transformed Earth. Much of its surface chemistry therefore offers access to an earlier stage of planetary construction. Earth followed another path. Accretion released heat. Radioactive elements warmed the interior. Impacts altered the young planet. Rock differentiated, gases escaped, crust formed, and eventually oceans covered large portions of the surface. Chemistry continued changing through interactions among water, minerals, atmosphere, and later biology. Arakoth never underwent that sequence. So, when you look at a distant, frozen body, you are seeing neither an opposite of Earth nor something chemically detached from it. You are seeing another outcome from the same reservoir of primordial material, preserved where temperatures remained low and sunlight stayed weak. That is what the dark worlds carry. They hold molecules assembled from elements that also became oceans, atmosphere, rock, and life here. Their unfamiliarity comes from what happened afterward, from billions of years spent under conditions Earth never experienced. We built instruments recently enough to begin reading that record. The objects themselves have carried it almost since the beginning, storing fragments of the solar system's earliest chemistry while Earth changed beyond recognition. Far beyond Neptune, the material remains, and some of it is the same ancient material that eventually became us. Beyond the last familiar worlds, there is no final marker. No boundary announces that the solar system has finished. The sun's domain simply thins across distances almost impossible to hold in mind, blending gradually into the interstellar medium and the greater architecture of the Milky Way. We have traveled far tonight, yet the worlds themselves continue without us. Sedna is moving toward the nearest point in its 11,400-year orbit. This passage happens once across a span longer than recorded civilization. No observer is required. For roughly 4.5 billion years, gravity has carried Sedna around the Sun through an orbit that crosses ages as easily as Earth crosses seasons. Farther outward, the scale becomes greater still. Across the Oort Cloud, perhaps 1 trillion icy bodies follow paths no telescope has directly mapped. Some move so far away that light requires more than a year to cross comparable distances. Passing stars disturb them. The gravitational tide of the Milky Way touches their trajectories. Occasionally, one begins an immense inward fall. Hundreds of thousands of years may pass before that journey ends near the Sunday. Then an object preserved in the outer reaches can brighten into a comet. Whatever civilization witnesses its arrival may be seeing material that began traveling inward before modern humans existed. That is the scale surrounding us. The darkness beyond Pluto contains frozen worlds, complex chemistry, unexplained orbital patterns, ancient surfaces, and remnants from the formation of everything we know. Some are cataloged. Others appear only through gravitational clues. Countless more remain beyond the sensitivity of the instruments we have built so far. Their existence does not depend upon discovery. Science has never required the universe to become understandable all at once. Every unanswered orbit, unexplained atmosphere, unusual surface, and missing population marks the present boundary of knowledge. Our maps improve because those boundaries can move. New instruments are arriving. Surveys are widening. Measurements accumulate night after night. Somewhere among incoming photons, stellar occultations, and orbital calculations may already lie answers that nobody has recognized yet. The sky contains more information than we have learned to extract from it. And beyond every telescope, the distant bodies continue their paths. They were circling before the first human looked upward and wondered what existed beyond the visible planets. They remained there while civilizations appeared, changed, and disappeared. They will remain long after tonight has passed. We entered this journey looking toward darkness and found that darkness crowded with history. The farther outward we traveled, the more the solar system expanded around us, until home itself became one small region inside something far older and larger. Those worlds have waited 4.5 billion years. They can wait a little longer. Rest now. The outer solar system will still be there when you wake.